Okay, hi everybody. My name is Pak Lui. I'm actually, going to present you some of the findings that I've been working on for the application, HPC application side. So in this session, I'm actually going to show you some of the results and findings that I've been using on the cluster that I have at the HPC Advisory Council for working on some of the application studies. So in the next 15 minutes, I'm going to be talking about some of those findings. I'm going to introduce you some of the application studies that we have worked on in the past. So there are approximately 160 applications that we have worked on in the past years. A lot of the findings and results actually are now hosted on the HPC Advisory Council website. The URL for those findings actually can be found there. So I encourage you to take a look if you want to look to find some of these studies for some of these HPC user applications. So and then we also have maintained it like a page that actually shows how to set it up and get your application running. So it will be useful for people who actually want to reproduce some of the results. So we add in some of the machine learning applications as well for setting up machine learning applications. Over the two of these applications that we recently added. And just to introduce you some of the HPC Advisory Council clusters that we maintained in the lab. And we have obviously the latest generation of the Intel clusters there. As well as also some hardware that we got donated by IBM for working on some of those studies. So later on, we have a couple of applications that we actually used, to show you the performance comparisons using the IBM systems. We obviously also have GPU clusters, but we have not, worked on. Well, we have not shown you that for today's session, but they actually were working on. I mean, they were being worked on for other applications that I'm not showing you though today. Just for the notes that a lot of the work actually is done is to help promoting the better performance on HPC applications. We're showing you by comparing different type of technologies in order to demonstrate which application or which hardware interconnect or hardware in general provides better performance and try to find out the reasons for that behind it. And we do comparisons in other things that may, justify for the performance differences. So the following slides actually shows you the type of the hardware that we have worked on. So we do have 3 of these clusters actually being used for these studies in the subsequent slides. So the first one is the 128 node, Intel Broadwell cluster. That actually has different type of network interconnect, namely the EDR InfiniBand and also the OPA hardware as well. And then we also have a second cluster that is the IBM Power 8 based, that is the Firestone cluster. The third one that we also going to show you in comparison for the last two comparisons on the applications is based also on the Intel cluster, but it's on the 32 node that we have for Broadwell. So GrowMax is one of the applications that we're doing it right now for comparison. So for GrowMax, we use the input data that's shown right there. That's actually based on the Praise benchmark, so it can be found there on their website. So we run the applications actually through different node sizes in order to compare the scalability performance. The metric that we use is called NS per day. Basically, it's the amount of nanoseconds of simulations that can be done on that input data in a day. So we try different versions of GrowMax in order to compare the performance, and for some reason we don't see much difference this version versus something that's slightly older. So I guess it's expected. We also run, comparisons with different network interconnect. So for this one, we are running across 128 nodes on the cluster with the same on the same platform. So we try two different network interconnect. One is the EDR InfiniBand. The other one is the OmniPath. So we show that we're able to see that better performance is actually with the EDR InfiniBand, both using actually Intel MPI as the MPI runtime. So the two of these technologies actually have different ways of being implemented. So OmniPath is an on-node based network architecture. This is basically using CPU cycles to process network traffic. InfiniBand is an off-node based that uses RDMA capability. So we can see that with the workload in here, we're able to see that better performance with the on GROMACS using EDR InfiniBand. Other comparisons we're actually doing right here is for GROMACS is that we try different type of transports in MPI. So Intel MPI do support a couple of the 2 or 3 actually different transports or it's called provider for network traffic for InfiniBand. One is called DAPL, the other one is the IB Verbs native. And then we also compared it with what OpenMPI has. So we do see that the native IB actually show better performance for the Intel MPI side compared to DAPL at scale. Just to analyze it, the type of communication that takes place for GROMACS in this input data, majority of the time actually spent in send and receive reduced. Only a fraction is in all reduced, which is the collective operation. So this is one of the reasons that I think this particular input data can scale, to that many systems because there's not a lot of time actually spent on collective operations. The second application I'm going to show you is called NAMD, which is another classical NAMD molecular dynamics code. In here, we actually show you the scalability of the NAMD with 2 different input data. One is called APOA1, the other one is called STMV. So with those are the input data, they can scale to 64 and 32 nodes. And we try different types of the MPI libraries. So we do see that there are difference as what we have saw in the previous previous slide, that different library, even with the same library, you can actually same MPI library, you can actually get different performance. So once again, we see that for some reason, like the first one, we're not able to show very good scalability up to 64 nodes for Intel MPI. HPCAC, that is based on OpenMPI, end up having slightly better performance on the first input data. The second one seems to be OFA provider, which is the IB Verbs support. So Intel MPI is pretty one of the it's one of the more popular commercial MPI implementation, but HPCAC is actually based on OpenMPI, which is also popular in some of the open source applications because it's free open source as well, the MPI library. Another slide actually is to show you the communication that actually takes place for NAMD. Approximately, I think like 95% actually of time for NAMD is spent on probing. So a lot of the non-blocking communication actually takes place, which is another reason that NAMD actually can enable to scale to many nodes because not too much of the MPI time is actually spent on collective operations. So this is one good way of actually understanding what's going on inside the communication library within the application. If you actually you actually see that a lot of the time actually spent on communications that is for collective operations, you tend to see that the performance on the scale would be actually limited. So this is one way to kind of justify it and to rationalize why some results that we're finding is what we see. The third application is called it's a benchmark. It's an open source supercomputing benchmark tool. That's called BSM Bench. So it's actually coming from, I believe it's the institute in the UK. It's a way of measuring performance on a supercomputer. So there's an institute actually coming up with this benchmarking tool. It includes actually 3 different tests in the BSM Bench for measuring compute and also a network and also a combination of both. So there are 3 different sets of tasks actually this BSM Bench is actually doing. This is actually to simulate a workload that's similar to an application like quantum espresso, or I'm sorry, this lattice quantum chromodynamics QCD codes. So as a way to understand the communication profiles for the BSM bench, we have worked on the MPI profiling as well. We compare against the three different type of workload that the BSM bench provides to us. So they are balanced, which is a combination of communication and compute. So we do find that all three of these actually show pretty much the same of the communication that that's happening underneath the hood. So a lot of time I just spend on variant or reduce, which are very also time consuming, and because they're collective operations. We were running this profile on 32 nodes, and as we actually scale to a higher node count, actually the communication pattern may change. But the overall part of the MPI compared to the overall wall clock time is still relatively small, because approximately about like 26 and 14% it actually spends on barrier compared to the overall time. The rest of the time will be computation. A snapshot of what type of messages being used in BSM bench is that you can see that a lot of non-blocking messages actually happen at the very high buffer sizes. They're in the order of like 128 meg and 256 meg and 512 megabytes per of the messages. So they are very large messages. So a high throughput network interconnect is actually very essential for the performance on this work benchmark. Similar information right here. I guess I don't have much time, but here we actually showing you the performance comparisons with two different network, interconnect MPI libraries. We do see not much of a change between the two, but the HPCAC MPI libraries actually show a little bit better, very slight performance. And we're here, we're actually using a switch of the hardware, but we're using the IBM Power Open Power 8 CPU. And we try different types of what they call it as the hardware threads. So imagine that you have a system with 20 cores, hardware cores. Each one of these hardware cores actually allows you to run additional threads in IBM architecture. So you can go from all the way from one hardware threads to 8 in order to expose more cores to the user to use. So what we actually have found is that by using or being able to more hardware threads, you do actually see better performance. So it's about up to 23% of the performance gain actually you can see by using hardware threads up to 4 threads per core. So if you actually give this, in the context of how it actually compares with Intel architecture, we actually also show you that with the E5-2697B4, 8B4, which is Broadwell CPU with 32 cores per node at 2.6 gigahertz, compared to what we have at the IBM, that is 20 core, but at running a high clock speed. So the performance difference is actually, it's actually a bit right here, high, because you actually can see that it's about 20% of the performance gain by having the IBM core on a single node basis. And the same trend actually is seeing across 2 and 4 nodes as well. So just a summary from what we have talked about. The fourth application or benchmark that I actually wanted to talk to you about is something called HPCG, which is an effort that is one of the potential benchmark to replace the HPL or LIMPAC that they're proposing is the high performance compute conjugate gradient, benchmark. In here, we also once again showing you the differences by using different types of different numbers of SMP threads. So from the IBM system. So Because of the additional cores, we actually are able to make use of to get better performance on the IBM system. I think this is one of the reasons. Another reason is that I believe that the Power system have better memory throughput. So by actually adding more cores in, you're able to exercise the remaining and additional memory throughput that has not been used by using single process per core. So you're scheduling more processes to the same hardware core. You're able to fill up that memory bandwidth gap, and also to fill in the pipelining for the instructions for the IBM Power 8 architecture. So it appears that we actually get able to use the last bit of the performance when we actually use the SMT threads to 4. So rather than using the only one hardware threads, we get about 45% of better performance by getting more cores into the. On a single node basis, this is what we are looking at compared to the x86 side. So we actually do see that slight improvement, about 8% of the performance gain by using IBM versus the x86 with the SMT 5 that we have shown you in the previous slide. This is a way of trying to see what we can do to improve performance on HPCG. So obviously, HPCG does require you to run for a certain time in order for the submission. To submit your result, you have to run it at least for 30 minutes before you can actually have a valid run. But the amount of time actually spent for HPCG does not actually matter because you can run for 5 minutes versus 30 minutes. The performance that you get for the gigaflops per second will remain the same. It's just that for qualification purposes, they actually want you to run for 30 minutes. And one other parameter that you can give it to HPCG as an input is the amount of the local matrices, matrix size that you tell the application to run for. However, we actually do not see much difference by using slightly higher or lower matrix sizes. It would be really different if you actually dropped it to a really small matrix sizes, like something that you can fit easily into the CPU cache. Then the performance will be very much different. It will be very much higher performance than what you can see from here. But it will not be considered as a valid run. So this is something that we have also found, but I'm not showed you in the slide here. Just one profiling slide on MPI communications. We do see that relatively to the overall runtime, the MPI portion of it is still relatively small. It's about like 1.5% or so. I think this is what I have for today, according to the time. So thank you very much.